Modifying trigonometric ratios into trigonometric functions. Trigonometric ratios, now we will redefine them into trigonometric functions. For that, the angle need to be drawn in the standard position. An angle is drawn now in the standard position whose measure is theta. An angle in standard position means this angle theta is drawn with one of its arms taken on the positive direction of x-axis with the vertex at the origin and the terminal side depending upon the value of theta, but measured in the anti-clockwise direction. From the x-axis, go anti-clockwise. Now, let us take a point on this terminal side. Point P, x, y. P, x, y is any point on the terminal side of the angle theta drawn in standard position. Then, this point P's distance from the origin O can be calculated by using coordinate geometry distance formula. OP is equal to root of x minus 0 whole square plus y minus 0 whole square. That eventually is x square plus y square under the root. That is the length OP. Let me call it R. The distance OP is R. Now, here we have three numbers x, y and R. X and y are the coordinates of the point taken and R is the directed distance of that point from the origin. So all these three numbers depend on the P that you have taken. Now these three numbers, all possible ratios I'm going to write. Ratios of x, y and R. The possible ratios are y upon r, x upon r, y upon x, x by y, r by x and r by y. These are the six possible ratios. They are respectively named sin theta, cos theta, tan theta, cot theta, sec theta and cosec theta. Now look, these are the new trigonometric functions of the angle theta. Trigonometric functions are defined for an angle theta drawn in the standard position. Notice that no right triangle is required. No right triangle is used for this definition. Trigonometric functions are not defined on the basis of any right triangle. Now, what is used is one point on the terminal side. Any point on the terminal side. But will these trigonometric functions values remain same if we had taken the point some other point? Angle is the same. So let us discuss that case also. If we had taken another point Q with coordinates, some other coordinates x1, y1, of course the distance from O to Q will also be different, not R. Let me call it R1, which also could have been calculated using these coordinates and 0, 0. Now we have three new numbers regarding this point Q. Two coordinates x1, y1, they are different from this x and y. The directed distance r1 which is not equal to this r. Then, using these three numbers, if we write the same six ratios, how will they look like? They will look like this. y1 by r1, x1 by r1, y1 by x1, x1 by y1, r1 by x1 and r1 by y1. Now the question is, the sin theta would be this for someone who has taken the point here. And sin theta for the same angle theta would be this ratio for another person who has taken the point here. But will this sin theta have same values? Yet to be checked. Are these two equal? Let's see. To know that, let's do a little more construction on this diagram. Drop two perpendiculars, one from P and one from Q, to the x-axis. The feet of the perpendiculars are M and N. Now, as the point P has coordinates x, y, this vertical distance is y. And this is the y coordinate of the second point, y1, this height. Also, the OM, the length OM, will be the x coordinate because the point P is x comma y, the x coordinate and y coordinate. Also, ON is equal to x1 as the coordinates of xp, this point Q is x1. Now, consider the two triangles OMP, the small triangle, and the triangle ONQ, the bigger triangle. What do you think about these two triangles? These two triangles have something special. This angle theta is common to both of them. Also, the small triangle is right triangle. Here there is a 90 degree. Here there is a 90 degree for the bigger triangle. So, one pair of angles of the smaller triangles respectively equal to one pair of angles of the bigger triangle. So, by AA similarity, the two triangles OPM and OQN are similar. Hence, the ratio of their sides will also be equal. That is a property of similar triangles. So, we can say this y upon this r must be equal to y1 upon r1. What have we got? Y upon r is equal to y1 upon r1. Oh, that is good. So, even if the point was taken somewhere else, even if this x1, y1 and r1 are three new numbers, the ratios would be same. So, the sine theta for this angle will be unaffected by the point that you have taken. Any point would do. So, this definition is irrespective of the position of the point taken. Only thing is that point should be on the terminal side, anywhere on the terminal side of this angle theta. This is the definition of trigonometric functions. Now, let us consider the trigonometric identities, the few trigonometric identities that we have already learned in lower classes. One of them is sine square theta plus cos square theta is 1. Is it applicable or is it true for this new definition? Yet to be checked. We'll try to have a proof. Here we go. For the proof, I take the left hand side, sine square theta plus cos square theta. And according to the definition, sine theta is y upon r and cos theta is x upon r. Let me use these two ratios in place of sine theta and cos theta. So it can be rewritten as y upon r whole square plus x upon r whole square. Which means y square upon r square plus x square upon r square. Taking LCM, r square is the denominator, y square plus x square. But y square plus x square is equal to r square because of this equation, squaring both sides. So this numerator can be rewritten as r square. So we have r square upon r square, which is equal to 1. So this identity holds good for this new definition. Next identity is sec square theta minus tan square theta is 1. Again, let us use sec theta and tan theta as r by x and y by x on the left hand side. R by x whole square plus y by x whole square gives me x square the denominator, r square minus y square. Now what is r square minus y square? Go to the same equation. R square minus y square is x square. So the numerator is replaced as x square upon x square is 1. Yes, second identity also is true. One more identity of this category. Cosec square theta minus cot square theta equal to 1. Let us check whether it is true. Putting the definition of cot theta and cosec theta. And proceeding further, Taking LCM y square, this time it is r square minus x square in the numerator, which is equal to y square. So it is y square by y square, which is equal to 1. So all these three identities are true for the new definition, that is for trigonometric functions. Furthermore, observe, this y upon r and r upon y, they are reciprocal to each other. Y upon r, r upon y. Hence, sin theta and cosec theta will also be reciprocal. So we have this identity, cosec theta equal to 1 by sin theta. Similarly, cos theta and sec theta are reciprocal. Also, tan theta and cot theta are reciprocal.